A cannonball of an unknown mass leaves a stationary cannon of mass 100 kg with a velocity of 250 meters per second as shown in the diagram below. Consider the system to be an isolated system. 3.2.1. Define the term an isolated system. An isolated system is a system where the net external force acting on the system is 0. Then 2 marks for that. 2.2.2 state the principle of conservation of linear momentum in words. It says that the total linear momentum in an isolated system is conserved in both magnitude and direction. Then both magnitude and direction. All right. 3.2.4. What is the initial momentum of the system before the cannonball leaves the cannon? And it's 1 mark, so it's 0 because everything is stationary there. 2.3. Everything is stationary. That's because the objects are stationary. All the objects there are stationary, not moving. An object that is not moving does not have momentum. So if the momentum is mass multiplied by velocity, stationary object has a velocity of 0, and anything times 0 is 0. So we have 0 momentum there. 3.2.5 says if the recoil velocity of the cannon is 10 meters per second, calculate the mass of the cannonball. Now, very, very important there. By saying that 10 meters per second it's a recoil, they are giving us the direction of the cannon. It means the cannon will be recoiling back, meaning to the left. There will be recoiling to the left after the shot. Now we have 250 meters per second after, and then we are supposed to calculate the mass of the cannonball. All right, so we're going to be using the principle of conservation of momentum for 3.2.5. Say the total momentum before is equal to the total momentum after, and then we're going to be having the initial momentum of object A. Let's say this is the cannon plus the initial momentum of B, the cannonball. But because they are together before, let's just have an single one initial momentum of both the cannon and the cannonball, and then they are separate after. So it's the final momentum of the cannon plus the final momentum of the cannonball. So the initial momentum of both cannon and cannonball, A and B, will be the mass of the cannon plus the mass of the cannonball, the initial velocity of both cannon and cannonball because they are together before. So you have the mass of the cannon, the velocity after of the cannon, plus the mass of the cannonball with the final velocity of the cannonball there. Now we must choose a direction. We choose to the right as positive. It means that the 250 is positive, but the recoil 10 is going to be negative there. So let's substitute here. So we have the mass of the cannonball is 100. Cannonball unknown. That's what we're trying to calculate there. They're stationary before. The initial velocity of both of them is 0. The mass of the cannon is 100, and the final velocity after the recoil is 10, but to the left, so it's going to be a negative 10, plus the mass of the cannonball multiplied by its velocity 250 to the right there after. So here we have this multiplied by 0 over here, giving us a 0, and we have this and here negative 1000 plus mass of the cannon ball there. Transpose over to that side, this 1000 becomes positive, so it's 1000 is equal to mass of the cannonball multiplied by the 250. To solve, divide by 250, divide by 250, and the mass of the cannonball will be equal to 4 kg there. 1, 2, 3, and 4 there. So this one is out of 11 there. Okay.